So this is the actual formula for the intensity of light at an angle theta as a function of the central intensity and how far out our angle is. It's just equal to the maximum intensity times the sine of alpha over alpha, where alpha is just half the phase difference between the top and bottom ray. Or you could argue that's the phase difference between the middle and either side. Notice that phase angle is going to be proportional to the number of loops we go around, and so that means the fact that we're proportional to 1 over alpha squared is exactly what we predicted qualitatively. So we have this sine alpha over alpha. Now even though sine alpha has a 0 when alpha equals 0, alpha will also be 0 there. And the limit of this, the limit of sine alpha over alpha, as alpha goes to 0, is just 1. So we get just the standard maximum central intensity at the center. So let's look at what this pattern looks like for a variety of different slit widths. This is a slit width exactly equal to the wavelength. In that case, we don't get a sine theta equal to lambda until theta equals 90 degrees. So if I'd taken this picture all the way out to 90 degrees on either side, we would eventually get to the 0 point. But from negative 20 to 20 degrees, we get a fairly broad peak with only a little bit of loss. We'd lose about 40% of the intensity from 0 degrees to 20 degrees. So it's not that much of a loss. If instead I change it so that a sine theta equals 5 lambda, so now the slit width is 5 times the wavelength, then the peak is much less broad, drops off much more quickly, and we find a minimum already here between 10 and 15 degrees. And we have another maximum and almost to a minimum by the time we reach 20 degrees. So notice that's much narrower, much sharper peak. If I change so that a sine theta equals 10 lambda, then that first minimum moves up to about half as much as it was for 5 lambda. It's not exactly half as much, because sine theta is not exactly equal to theta, but for small angles it gets close. So it's about half as wide, so I have a much narrower peak, and now I can see 1, 2 maxima, and the beginnings of a third maximum to the side as we get out towards 20 degrees. Incidentally, this shows why we don't see these diffraction patterns easily all the time. If I talk about light coming through a window or through a doorway, then A, the slit width, is many thousands of times larger than the wavelength. If A is 1,000 times the wavelength, then we're going to have a tremendously small, narrow peak, and we'll see essentially no diffraction pattern to the sides. And that is why we were able to use ray optics throughout Chapter 34. It didn't matter that there was diffraction, because as long as we were dealing with large objects, the diffraction patterns were very narrow and could be ignored.